All right, welcome to our final design review for Senior Design 1. My name is Frank Sotera. Our team is Hydroponics, and we are planning to design a more efficient hydroponic growing system. In this presentation, we'll go through our objective, design constraints, our approach, and our test specifications. Here's our abstract that you can review on our website at a later time. Like I said before, my name is Frank Sotera. I'm studying mechanical engineering. On my team is Barbara Cushing and Matthew Dickinson, who are studying civil engineering, and also Victoria Goldman, studying environmental engineering. Our faculty advisor is Dr. Van Aken with the Department of Civil and Environmental Engineering. So a quick introduction to hydroponics. It's a method of growing plants in a soilless environment supplemented by water and nutrient solution. These methods are not new. They can be traced back to 600 BC with the Hanging Gardens of Babylon, and they have been improved upon in the upcoming centuries.
Excuse me, Frank, I don't want to interrupt, but you're not in the camera. Can you step aside? There's a remote.
Absolutely.
There's a remote clicker. What is the remote clicker?
All right, so we aim to improve on optimization by focusing on the three major aspects of hydroponic technology, looking at the lighting optimization, space-efficient design, and the active recovery system. We hope that through our efforts we can provide a more efficient design for a viable option for urban farming. So here's a table of some of our technical design constraints. We want to have an allergy-free system. We want a high-efficient light source that's also cost-effective, versatile design, crop density that can be comparable and surpassable to current methods, and a nutrient solution distribution system that implements an active recovery setup. As for our non-technical design constraints, cost-effective, we want to be as close to our allotted $500 budget, or as close as possible. When we're finished with the chemicals we're using for our nutrient solution, we want to make sure they're disposed in a safe way. We want a reliable system with materials used that will last the duration of our project. A design that's easy to maintain and build, and ideally we would like our crops being produced to be safe for human consumption. So right here we have a drawing, SolidWorks, of our prototype design. As you can see, it implements the vertical stack grow rings, and these surround a central lighting source right here. At the bottom we have a reservoir that will hold our nutrient solution. It's connected to an irrigation system. It's kind of hard in this picture, but it's hoses that run along the frame of our system. Each ring will have an independent supply and a return back into the reservoir. So a key to our versatile design would be a slotted frame for our shelving system. This will allow for a highly customizable shelving that will be stacked. We can control the height between layers, and also tilted layers within the frame themselves. This will be beneficial for an irrigation technique I'll get into in a little bit. We plan to build our frame with low carbon steel. It's inexpensive, high strength, weldable and machinable if need be. The next step to our versatile design would be the design of our grow ring. As you can see here, we have an octagonal shape. We will be building our design using PVC pipe. Also, it's inexpensive, durable, lightweight, and it's easy to work with. Ideally, when it comes to shape, we needed a shape that, since we're using a centralized lighting source, that would provide maximum even light distribution. Theoretically, a circle would be the most ideal shape to use for that, but when considering building a circular ring out of PVC, it would prove to be a little bit difficult. So since considering PVC pipes are sold in straight cylindrical lengths, so this narrowed our shape down to a polygon, and we concluded that the most circular and practical polygon to use would be an octagon. The next thing you might be asking is, we have a missing segment in our octagonal shape here. This is another aspect of versatility. If you look back at our system, these rings will be surrounding a centralized lighting source. So if they need to be taken out at any time for maintenance or testing, if it wasn't enclosed, you'd have to slide off each frame from the system. With this open side, irrigation can be independently removed, the ring can be taken out, and you can do what you need to do with it without disrupting the entire system. For our prototype design, we were told that with lab space we wouldn't have more than really 9 square feet to be working with. So as you can see here, our length or the width comes out to be about 34 inches. Even within our entire system, it comes out to be right under 9 square feet for lab space, using 12-inch segments for our octagon. So right here is a block diagram of how our system is proposed to be used. We'll have Our water and nutrients will be mixed together to form a nutrient solution, which is in our storage container. Also in the container would be an aeration device to oxygenate our solution, and also a water pump set up to a timer that will independently supply each growing with nutrient solution. After its cycle, it will be recycled and put back into the storage container. So a quick comparison to crop density of other methods. Looking at current farming practices, they have a plant density of about 2.44 plants per square foot, flatbed hydroponic yielding between 4 to 5 plants per square foot. And with our rings, we're looking at about 1.5 plants per ring. Using a 3-ring system would put us at 4.7, 4 rings being 6.2 plants per square foot, surpassing some of the competition out there right now. So for our testing and our prototype design, we'll be using butterhead lettuce, also known as Bibb lettuce. It's high in vitamin A, C, and K, and also high dietary fiber. It has a full maturity rate of about 65 days for its harvest period. And another reason why we're using Bibb lettuce is its growing requirements fit well to the size of our prototype. Plants can be spaced 4 to 6 inches apart, and they really don't grow higher than 1 foot. So allowing us, if we wanted to, adding layers with only 1 foot space is not that bad. They also grow well in partial and full light. So moving to our nutrient solution, this is what's going to provide our plants with the nutrients necessary to survive. Usually in normal growing, you would get that from the soil, but since we're in a soilless environment here, this will be supplemented. For nutrient solution, the 3 main nutrients, or the macronutrients we'll be looking at is nitrogen, potassium, and phosphorus. These will be used in the most amounts. The solution is a mix of water and nutrients. And along with the 3 macro, we have several micronutrients that are used in smaller amounts, but they're still vital for plant growth. This table here represents different scientists throughout the decades, what they believe is the best combination of nutrients to a solution. These values are milligrams of nutrient to liter of solution. We plan to be we're designing our own solution, and we'll be looking at these values when designing our own solution. Next, we're looking at our growing medium. Since we're not using soil, the growth medium here, they provide water, oxygen, nutrients, and support for the roots, much as the soil would. They're categorized by particle size, shape, and porosity. Different irrigation techniques will use different types of growth mediums, and also different plants have different types, and we'll go into that in a little bit. So looking at our lighting source, we're proposing that a centralized lighting will provide light to more plants than conventional overhead lighting. 2 of the main components for photosynthesis is chlorophyll A and B, and as you can see here, they are maximized when in a wavelength of about 400 to 500 nanometers. And again, they peak in about the 650 to 700 nanometer range. When in the violet-blue range, this promotes vegetative growth, and in the orange-red range, promoting fruiting. Since our Bibb lettuce is mainly vegetative growth, we'll be looking for a lighting source that focuses in the 450 to 500 nanometer range. Here are some of the bulbs that we're planning on using. We're looking at T5 fluorescent bulbs and also compact fluorescent bulbs. And you can see here from this table that each of those, at their color temperature, they're putting out 6,500 Kelvin. And looking at this next chart, looking at the 6,500 Kelvin range, they're peaked in the 400 to 500 nanometer wavelength. So those should be well for our system. Moving on to our test specifications, the overall goal of our testing is to determine which factors will lead to the most biomass at the most cost-effective way. The 2 major factors we'll be testing is our methods of nutrient solution distribution and our lighting configuration. The 2 methods of irrigation we'll be testing are ebb and flow and the nutrient film technique. For these tests, our plant type and lighting source will be a constant variable, making biomass totally dependent on the irrigation method. For these tests, we'll be monitoring a harvest period using each method, and throughout that harvest period, we'll be recording biomass every 2 to 3 days. And since we're using an active recovery system, meaning that our nutrient solution will be recycled and reused, we need to be careful and watch out for nutrient depletion. All right, so for the ebb and flow method, it's a simple flood and drain system. We'll have a pump in the reservoir that will pump solution up to our rings. For the flooding period, it will fill the full volume of each grow ring. The solution will sit in there for 20 to 30 minutes, and then it will be drained, recycled back into the reservoir, and this cycle will be repeated throughout the day. A growing medium for our ebb and flow method, we're looking at cocoa coir, which is a fiber-like block made from the leftover husk of coconut. These are viable because they're porous, which allows good aeration, and they retain water and nutrients well. The only problem with these are that they deteriorate pretty fast in a little bit of time. To help that, we can supplement it with lightweight expanded clay aggregate, and that will help prevent it breaking apart and floating away, potentially clogging our system. Looking at the nutrient film technique we'll be comparing to, instead of using a constant flow, or a flooding period, here we'll have our grow rings on a slight tilted angle, and throughout the period, just a thin layer or a film of solution will run along the bottom of the roots of our plants. A growing medium isn't required for NFT to allow the plant growth, and nutrient solution will run through the system up to 24 hours a day. Since a growing medium is not necessary, it is useful in early growth to stabilize the fragile roots. Some of our research has pointed towards using rock wool for the growing medium for this phase. It's melted down basalt rock and it's spun into a fiber. We plan to grow our plants in this for about 2 to 3 weeks before we transplant them into our system. Our water flow, looking at each of our octagon, each side is a 12-inch cylinder, 4-inch diameter. That puts us at 4.5 gallons per ring. Using a 3-ring system, we'll be at 13.7 gallons, and 4 rings will put us at 18.28 gallons. Looking at our ebb and flow method, where we'll be filling our system complete volume every half hour, that puts us at a rate of 36.5 gallons an hour. The pump we plan to use is the MaxiJet 500, rated for 110 gallons per hour, which will be more than sufficient. So like I said, since we're using active recovery, we need to monitor our nutrient depletion. We can do this by monitoring pH, oxygen levels, temperature, and electrical conductivity. The pH gives us is an indicator of how acidic or alkaline our solution is. We want to be within a 6 to 6.5 range for this, and if it's too high or too low, this can stunt plant growth, and it can be adjusted using nitric, sulfuric, or phosphoric acid. The salt oxygen levels determine whether the solution needs to be more or less aerated. It can be monitored using a DO meter, temperature with a thermometer. Lastly, with electric conductivity, the total ionic concentration of the nutrient solution determines growth, development, and production of plants. We want to be at a range of 1.4 Siemens per meter with lettuce, and if all these variables, they have an allowed range, and if we're outside of that, that can show nutrient depletion. So with those two testing, we can get a standard S-curve for biomass versus time. The bottom curve is derivative of that line, showing the rate of biomass change, and each method will produce its own curve, and we can determine which is more efficient through that. After we have the successor of those two tests, we will test our lighting configurations. We'll be testing overhead versus centralized lighting. Biomass will be compared to energy usage to determine efficiency. Here's just a sample data collection that we plan to do. We'll have 2 sets of centralized lighting and 2 sets of overhead. We'll compare the biomass in kilograms compared to the energy usage in kilowatt hours to determine its efficiency. So a couple of risks that we see in our design that we can face is a vertical design. They're relatively new. There's not a lot of research done on them right now. With our vertical light source, it's non-standard. It will require a custom ballast. We need proper ventilation since it will be an enclosed system with a lot of heat from lights. We do face under budgeting with only $500 budget, and we do need to watch out and have an algae-free system because it decreases the dissolved oxygen and increases biochemical oxygen demand. Algae itself is not a problem, but it does attract undesirables into our system. Here's a schedule that we've done throughout our Senior Design 1. Quick cost basis that we put together puts us at $700, which is pretty close to our allotted budget. So we are looking for secondary funding. Senior Design 1, this is what we've gone through. Right now, we're looking for secondary funding, like I said, and in the next 2 weeks, we hope to start building a prototype. In Senior Design 2, we hope to test the prototype, improve upon it, and find sponsors. Thank you.
Any questions? You guys are doing really good this afternoon. Nobody has any, oh, somebody has a question?
For nutrient depletion, is pH the only thing you test for, like what's involved like in the nutrients of your solution?
Well, we're going to be monitoring like the pH level, the dissolved oxygen, and electric conductivity. And with those variables, if we fall outside of the range in those testing, that will show us that we possibly need to redo our nutrient solution.
What sort of nutrients do you plan to include in your nutrient solution?
The nutrients that we're looking at, like I said, the three major ones are going to be, is it right there, potassium, nitrogen, and phosphorus, and then there's also a couple micronutrients used in smaller amounts right here.
Other questions?
Well, that's a good question because indeed I think you should refine a little bit the monitoring because the conductivity, it not, alone will not give you an indication of what specific nutrient are needed more than another. I have actually a question that you, so you plan to build a system in PVC. Is there any problem with PVC when it comes to produce edible products?
Not to our knowledge, PVC seems to be a common use in a lot of hydroponic systems.
Okay. So it can release actually vinyl chloride,
Yeah.
which is very toxic. But you should indeed, you should include an additional quality component, which is related to what is approved and not, and basically all other aspects as well. For instance, the plant that we are going to grow, you wouldn't be able to eat them because they will be produced in a lab. So that's the first thing. But for the test, for the purpose of testing a prototype, I don't think it's a problem. But I think for further development, you have to be sure that every component here, are actually approved by FDA, and because there is a supplemental, constraints there.
Yeah, there's something we have to look into. Yeah, because you said before that we can't actually eat anything produced in the lab, but after we take it outward, we want to make sure it's safe.
Other questions? I've got a couple of comments or questions, I guess, and again, I go back to the nutrients. I'm not convinced that your sampling plan for nutrients is adequate. I'm looking at here a dozen or a half a dozen or a dozen nutrients, any one of which could become depleted and result in reduced plant growth, and unless you're analyzing them, you're never going to know.
Yeah.
The other aspect of the nutrients is you talked about adjusting the pH using nitric or phosphoric acid. That's going to affect your nutrient ratios. If you add phosphoric acid, you're adding phosphorus. You could, in fact, you're going to have an impact on your nutrient concentrations, and you haven't addressed that at all. And I think that needs to be addressed.
Yeah, monitoring our solution, the nutrient depletion is probably going to be one of the hardest parts of our project.
Okay. The other question I had was regarding the pumping. You showed some calculations where you needed to have a 36 gallon per hour flow rate, something like that.
Yes.
And you decided to use a pump that has a 110 gallon per hour flow rate?
Just looking at standards, we figured we need a minimum of at least 36. And looking at standard pumps on our from the website, 110 was one of the cheapest, and it got good reviews, and we figured it would be more than enough.
And these pumps are going to direct the water directly into
each ring.
Into each ring. Is there a concern with the input velocity with the ebb and flow, where you're filling it up, you're letting it sit there, and you're draining it out? Are you concerned about having the velocity as you're filling it being too high, where you might damage the roots?
I guess as of right now, we're not sure what the velocity is going to be. It's going to be something through testing that we have to calculate.
Okay.
I don't know if it's adjustable through that, but it is something we're going to have to look into.
Okay. And in terms of the light levels, are you going to measure the light output, or are you simply going to take the values off the light bulbs or light boxes?
As of right now, just the values that were given for that.
Okay. You might want to look into what it would take to get light measurements.
Okay.
Because the bulbs will, their output will reduce over time, fluorescent lights. So you might want to be able to measure that.
No, that's easy to do. We have a meter with the lab, so that's not.
Okay. I don't have any other questions. Anybody else?